Hello, our new topic is bending. Now we have seen the axial loading of structures. Now, of course, this is not the only type of loading. So we may have transverse loading of structural members. Let's consider a beam in order to see how it happens, and let's assume that it is simply supported. And we have a force at an arbitrary location, a transverse force, which is perpendicular to the structural member. Now what we expect is, under this force, this beam will make such kind of a deformation. So it will be deflected because of the force. Of course, what happens inside the beam is, just assume that beam is made of very small strings. Infinitely small strings. Now, under this force, what you expect is, I will just draw an axis at an arbitrary location. It has a certain purpose, so this I will explain it later, why I draw the axis at an arbitrary location. So, under such kind of a force, when the structure is subjected to such kind of a force, the strings at the top of the beam will be contracted. This is what I expect, because the distance will get shorter and the strings at the bottom will be elongated. Therefore, I can easily say that beam is subjected to a compressive force or compressive stress at the top and tensile stress at the bottom. So if this is my beam, this is what I expect to see. So I have compressive force, compressive stress, since the deformation is caused by the stress, and I have tensile stress at the bottom. This is what the case is. And in fact, there is a point on which the stress is zero. Certainly, this set of points is called neutral axis. So neutral axis is the axis on which the stress is zero. So how could it be possible that you have a transverse force and certainly it causes a stress in the normal direction? Now let's see what happens in the beam. Now just draw the beam again. And let's define the coordinate system. X as the horizontal and Y is the vertical coordinate. And let's take an arbitrary location on the beam, X, and just make a very small increment to this location, delta X. Therefore, I just take a thin slice which has a thickness of delta x, and I put my axis on this x coordinate on this axis. So I choose x coordinate, x-axis coincides with the neutral axis, and in fact I choose the y coordinate perpendicular to it. Then what I'm going to do is I just will take an arbitrary location with a distance of y from the neutral axis. Certainly at this point the thickness of this thin slice will be delta s. So certainly delta s is equal to delta x. Okay, now this is the undeformed case, and let's look what happens in case of deformation. We apply a force, and at this particular location beam is curved then, and of course this thin slice deforms. Now it makes a curvature. Let's say that locally it acts like a circle. On the neutral axis I have zero stress. As a result, the thickness does not change, it is delta s again. But for the arbitrary location y, it is delta s prime. Now let's say that this local circle has a radius of rho. We call this radius of curvature, which we have seen in the calculus. And let's say that the surface of the beam has a distance of c from the neutral axis. Now let's calculate the delta s prime and delta s. Certainly this thin slice will make a small angle delta theta. Therefore I can write the delta s prime. It is rho minus y multiplied by delta theta, and delta s is equal to rho multiplied by delta theta. Now I can write the strain. Strain is equal to rho minus, so delta s prime, I'm just calculating the strain at particular location of y. So rho minus y delta theta minus rho delta theta divided by rho delta theta. From here I can easily calculate the strain. It is minus y divided by rho. Now I have to calculate the radius of curvature, but in fact in order to eliminate it from the from our equations I will use another approach. In fact I know that I see the maximum strain at on the surface of the beam. either at the top or at the bottom. In fact, let's say that this maximum is on the top of the beam, and let's say that it has a distance of c. Now the magnitude of the maximum strain then is equal to c divided by rho. Therefore, I can easily write the relationship between the strain and the maximum strain as minus y divided by c. So this is my expression. So I establish a relationship between the strain at an arbitrary location and the maximum strain which occurs on the surface of the beam. That's okay. Now, next we need to establish a relationship between the externally applied load and the stress. So, for this purpose, first I will write the force equilibrium. In fact, when you have such kind of a thin slice, you have stress on the surface and moment acting on it on both sides. Certainly it has to be in static equilibrium, and in fact you have the stress distribution. And as we see, stress varies linearly since the strain changes linearly. In fact, I can establish a relationship between the stress. So remember that stress is equal to Young modulus multiplied by the strain. In fact, maximum stress is equal to also Young modulus multiplied by the maximum strain. So the maximum strain and maximum stress is by means of magnitude, in fact. So it can be compressive or tensile. So I omit the sign. Anyway, from here I can easily say that ratio of the stress at particular location of y is equal to minus y divided by c. Okay, now these are my expressions. Now let's write the force equilibrium on the surface of this thin slice. Therefore, what I'm going to do is I will integrate the force on the cross section. Now just assume that this is my cross section. I just take a tiny piece, a unit area, infinitely small area, and let's assume that neutral axis is located somewhere here. I'm sorry, this is area, by the way. Okay, now I know that for this particular area, dF is equal to sigma dA, so stress multiplied by the area. So area is equal to sigma dA. Now, instead of sigma, I will put the relationship between the maximum stress and stress at a particular point. So this is equal to minus sigma max divided by C multiplied by EA and integration over the area. And this is, since maximum stress is constant, independent of the area, I can take it outside the integral. This is y dA, and this is equal to 0 because sum of the forces has to be equal to 0 in the normal direction. Now this tells me something. Now sigma max has a finite value, that's also okay. C has a finite value, and the only way that this expression is 0 is the integral is 0. Or in other words, let's write it here. Y dA is 0. So first moment of area is 0. So what it means? So this basic, so remember that geometric center is equal to Y dA area divided by dA. So this is how we calculate the location of the resultant force, remember? And in order, since Y dA is equal to 0, this is equal to 0. Now Y bar was the geometric center, and this basically means that neutral axis coincides with the centroid, or in other words, neutral axis is the centroid. Is on the centroid. Of the area. Okay, now this is our first expression. In fact, this is critical. Therefore, in order to find the neutral axis, we need to find the centroid of the cross section. Now we need to establish a relationship between the moment and force. So we have the moment, and at a particular location, certainly this stress, as you see, it will generate a force couple, because stress is force per unit area, and it will tend to bend the structure. As a result, we have a bending moment. In fact, on the cross section, static equilibrium conditions has to be satisfied, which means that sum of the moments has to be equal to 0. Now, if we say that at this particular location moment is m of x. It is the has to be equal to m of x plus y df. So this is the moment, has to be equal to 0, or m of x equal to minus y df. Now df is equal to minus y sigma df, sigma dA, sorry. This integral is over the area, and as a result I can write the sigma by means of maximum stress, stress at a particular location by means of maximum stress and where it occurs. So this is integral over the area. This is minus y, sigma is equal to minus y divided by c multiplied by sigma max dA. From here I can, since c is constant, maximum stress is constant, I can take it outside the integral. Sigma max is equal to sigma max divided by c integral y square dA. Okay, now as we see, moment, bending moment at a particular location is a function of the cross section at this particular location, maximum stress and distance of the outer surface or surface of distance of neutral axis and distance between the neutral axis and the surface. Okay, so this is what how I calculate how we can derive the expression. And now we establish a relationship between the stress and bending moment. Now we can say that I is equal to y square dA. This is called bending moment of inertia, or second moment of area. We will see how we are going to calculate this expression. Therefore, we can easily write the bending moment at a particular location as mx is equal to sigma max divided by c multiplied by I. Now, if I want to write the stress, I can write it like this: sigma max is equal to mx multiplied by I divided by c Now I can substitute the expression for the sigma. If I substitute the expression, sorry, this is not like this, I made a mistake. This is C and this is I. So sigma is equal to stress at any location is equal to m of x multiplied by y divided by I. So this is my formula for the stress at arbitrary location. I is the bending moment of inertia, m is the bending moment at that particular location, and y is the coordinate. Okay, now this is our flexure formula. Okay, now let's see some properties of bending moment of inertia. So let's consider an arbitrary cross section, and in fact we choose let's say that this is z coordinate. In fact, we put the origin of our coordinate system on the centroid, and for this arbitrary cross section what we did is we take an infinitesimal area and we say that bending moment of inertia I is equal to y squared dA. Certainly this is bending moment of inertia with respect to z-axis for this case. Okay, now let's see what the case is if we want to take the bending of moment of inertia with respect to another axis. Let's say that this is z prime. The distance between z and z prime is, let's say, d. Now we have another coordinate system. In this case, the bending moment of inertia by z prime is equal to let's write it here. Bending moment of inertia Iz prime is equal to integration over the area y plus d square dA. Now if I expand the expression in parentheses, this is what I am going to get. This is y square dA plus 2d while dA plus d square dA. Now this is Iz, this is the bending moment of inertia with respect to the z-axis. Now this is first moment of the area, and remember that since I choose the point O, just on the centroid, this is equal to 0, and this is the area of the cross section. Therefore, if I want to translate if I want to calculate the bending moment of inertia with respect to another axis, it is equal to bending moment of inertia with respect to the axis that we have calculated previously, plus area multiplied by the square of the distance between two axes. So this is the general formula. Here this can be applied to any type of cross section. Again, we haven't made any assumption on the geometric properties of the cross section. It's okay. Now, second thing is, what if we want to calculate the bending moment of inertia of the hollow, of an hollow cross section. Let's say that we have a cross section and let's say that this is A1 and this is A2. Certainly they have bending moment of inertia their bending moment of inertia can be calculated with respect to the centroid, and let's say that we have the centroid at an arbitrary location O, and let's say that this is Z, this is Y, then bending moment of inertia of the system is equal to Iz1 minus Iz2. So we subtract the bending moment of inertia of the hollow part from the complete bending moment of inertia of the area covered by the outer surfaces. So these are the two important properties of bending moment of inertia. Now let's calculate the bending moment of inertia of a square. Now let's have a square. Cross section. Certainly its centroid is located at the center. It is Z, it's Y. It's straightforward to calculate. This is O, and let's say that its width is B, and it has a height of h. What I'm going to do is I will just take a thin slice at a distance of y, so it has a thickness of dy, therefore area of this thin slice is equal to b multiplied by dy. Now let's calculate the bending moment of inertia. This is area y squared dA. In fact, if I substitute this expression for the dA, my bounds for the integral is minus h divided by 2 to h divided by 2. This is y square b dy, and then b is constant, it will come out, so this is integral is b y cube divided by 3 from minus h divided by 2 to h divided by 2, and in fact I can calculate the bending moment of inertia of a square cross section, of the rectangular cross section with respect to its centroid is b h cube divided by 12. Now, how about it is bending moment of inertia with respect to it is bottom edge. I put in another coordinate system z prime. Let's calculate the bending moment of inertia with respect to this axis. So this is Iz plus area multiplied by square of the distance. Iz is equal to bh cube divided by 12 plus area is equal to b multiplied by h. This is the area of the rectangle, and distance is h divided by 2 square. From here I have bh cube 12 plus b h cube divided by 4. Then what I'm going to have is b h cube divided by 3. This is the expression for bending moment of inertia of the rectangle with respect to its bottom edge. Okay, now what if we have a hollow cross section? Again, I will continue to work on a rectangular cross section. Just assume that we have such kind of a rectangle. So let's say that its width is b, its height is h. Then I assume that I have such a hollow part here. So this will be my cross section. In fact, I can calculate the bending moment of inertia of this cross section. So let's say that this distance is h divided by 3, and this distance is b divided by 3, and this distance is h divided by 3. So Iz is equal to Iz1, so this is 1, minus Iz2, so this area is 2. In fact, Iz1 is equal to 1/12. We have just calculated b h cube. Now this part has a bending moment of inertia with respect to its bottom edge, so the bottom edge coincides with the z-axis. It is 1/3 b divided by 3 multiplied by h divided by 3 cube, and from here 1/12 b h cube, this is 3 to the power 4, 3 to the power 5, and it makes 343. And from here the result is bending moment of inertia for this cross section 77 divided by 972 BH cube. So this is just an example for calculating the moment of inertia or bending moment of inertia for a cross section. Hello everyone, our problem is 649. Question is like this: determine the maximum tensile and compressive bending stress in the beam if it is subjected to a moment of 6 kilonewton meters. Now we have a T-like cross section as is seen in the figure, and we have a bending moment. Magnitude of the bending moment is given, and we are asked for the maximum tensile and compressive bending stresses. Therefore we need to first calculate the centroid of this cross section, or in other words where the stress is zero, neutral axis. Now we will begin by defining our variables first. First we will define the variables for the problem. Let's draw the cross section again. It is symmetric. Okay, so let's say that this is T, and then we have this distance. Let's say that this is H1. Then we have this distance. This is H2. This distance is again T, and certainly we have this dimension. This is H1, and this is T, and of course this is T. Okay, so this is our cross section, and our cross section is made of 4 areas. So let's say that this is A1, this is A2, this is A3, and we have A4. These are the areas which forms our cross section. Now next we need to define a reference for our coordinate system. I choose the bottom of the cross section as my reference, so I put my origin to the bottom of the coordinate system. Okay, now I will calculate the centroid first. So y bar. Y bar is equal to moment of the areas, sum of the moment of the areas divided by the total area of the cross section. So basically, if each area has the centroid, so this is y1, so this is y4, this is y3, and sorry, this is y3, this is y2, and this is y4. Okay, so this is basically a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3 plus a4. Now let's write it. Let's a1 and a2 are identical, therefore I only need to write the moment of the area either a1 or a2. So it is, the area is h1 multiplied by t. The centroid is located at h2 minus h1 divided by 2, right? Because I just put the coordinate of it, and the coordinate of the centroid of a1 with respect to the reference point. So this is the coordinate of the centroid with respect to the reference point, and I choose the bottom line as my reference. Okay, so plus, now coordinate of y3, it is first the area is h1 plus 2t multiplied by t, because it has a thickness of t, multiplied by h2 plus t divided by 2 plus moment of the area of 4. The area itself is h2 multiplied by t, and its geometric center is h2 divided by 2, located at this coordinate. And then we divide it by the area, total area. The total area is 2 times h1 multiplied by t plus h1 plus 2t multiplied by t plus h2 multiplied by t. Okay, so this is our centroid, and from here you find the value. You can do the calculation, in fact, by means of meter. Next thing is we have to calculate the moment of inertia of this cross section, bending moment of inertia. Now we need to calculate it with respect to the centroid. So y bar is somewhere here. So this is the, let's say, centroid of the total cross section of my beam, and then I need to calculate the bending moment of inertia with respect to the axis which passes from this point. Therefore, what I'm going to do is I will calculate the moment of inertia of each area with respect to this axis, and then I will sum them in order to find the bending moment of inertia of the cross section. So bending moment of inertia of the cross section is bending moment of inertia of the first area plus the second one plus third one plus fourth one. Now bending moment of inertia of the first one is, first area is, first I will calculate the bending moment of inertia with respect to the centroid. First I will begin from A1 and A2. So I have 2. Bending moment of inertia of a rectangle is, with respect to its center, is 1/12 t multiplied by h1 cube. Then this is with respect to, this is the bending moment of inertia with respect to this centroid, plus area t multiplied by h1, then distance of its centroid to the centroid of the overall cross section. So remember that its centroid is located at h2 minus h1 divided by 2 minus y bar and square of it. Okay, now I will write, or let's continue here. I will write the bending moment of inertia of the third area. It is 1 over 12 multiplied by 2t plus h1. This is the width, multiplied by t cube. This is the height, plus its area, 2t plus h1 multiplied by t multiplied by distance of its centroid to the centroid of the overall cross section. So centroid is located at h2 plus t divided by 2, and its distance is minus y bar, that is the square of it, plus fourth area. This is the 1 over 12 multiplied by t h2 cube plus h2 multiplied by t multiplied by h2 divided by 2 minus y bar square. From here you have the value for the bending moment of inertia. Okay, now I find the bending moment of inertia. In fact, when you have such a bending moment of inertia, you have two stresses. Of course, what you expect is, in this case, you see the maximum compressive stress here at this point and maximum tensile stress here. Now let's calculate the maximum compressive stress. That is minus m multiplied by the distance of this point to the centroid. This point has a coordinate of t plus h2, and distance to the centroid is t plus h2 minus y bar divided by I bending. This will give us the maximum compressive stress by means of pascals, and in fact we can calculate the maximum tensile stress. Maximum tensile stress is equal to, it is located at the bottom. So here, remember that in our formula for the flexure, our reference coordinate is always on the neutral axis. Therefore, according to an axis on the neutral, according to the axis which passes from the centroid, this location is minus y bar, this distance is minus y bar, and we have another minus coming from the equation, and therefore this is positive m y bar divided by I bending. This gives us the value for the maximum tensile stress. Now our problem is 652. If the beam is subjected to an internal moment of 30 kilonewton meters, determine the maximum bending stress in the beam. The beam is made from A992 steel. Sketch the bending stress distribution on the cross section. Okay, now we are given a bending moment and we have an I-beam as is seen from the figure. It is symmetric. The dimensions are given. So first thing that we need to do is to define the variables for the dimensions. Let's sketch the cross section first. We have an I-beam. Okay, so we are given that this thickness is 10 millimeters. So let's say that this is T2. T2 is 10, and then we have the other thickness here, T1. T1 is 15 millimeters. This distance is given as 50 millimeters. Let's say that this is B, and we have another 50 here. That's okay. And this distance is given as 150 millimeters, and we will call it H, and that's equal to 150 millimeters. Okay, again we will begin by choosing a reference point for the solution. So let's write the variables first. Again, this is, we have H is equal to 150 millimeters. We have B, that is 50 millimeters. We have T1 is 15 millimeters, and T2 is equal to 10 millimeters. These are our dimensions. Now we need to calculate the bending moment of inertia. So of course here we have an advantage. We don't need to calculate the location of the centroid. If you calculate the location of the centroid, you obviously will find that it is located just at the center, because the cross section is symmetric. In fact, as a result, I will just calculate the bending moment of inertia. Bending moment of inertia for this cross section is, first I have two areas at the top and at the bottom. So this is 1/12 multiplied by its width 2b multiplied by t1 cube plus 2b t1 and distance to the centroid. So distance to the centroid is equal to h divided by 2 minus t1 divided by 2. So because this distance is h divided by 2, and I will subtract this distance in order to find the centroid of the cross section. These are the bending moment of inertia of the upper and lower parts. Plus, now I will calculate the bending moment of inertia of the central column. So this is 1/12. This has a thickness of T2. Its height is h minus 2 T1 cube. So this is the bending moment of inertia. Then if you put the values, you will obtain, if you put the variables into its places, you will obtain the value for bending moment of inertia. Okay, so this is the bending moment of inertia for this cross section. Now if I look at the cross section, obviously I will see that I will see a compressive stress at the top and tensile stress at the bottom. Since the cross section is symmetric, the maximum tensile stress is equal to maximum compressive stress. Therefore I only need to calculate either of them, doesn't matter. Indeed, I will omit the sign in the stress, in the equation for the stress. So maximum stress is equal to moment multiplied by distance to the centroid, that is h divided by 2 divided by I bending. Then you will obtain the maximum stress from here. Hello. Our next problem is 655. So let's read the problem. If the built-up beam is subjected to an internal moment of m is equal to 75 kilonewton meters, determine the amount of this internal moment resisted by plate A. So we have T-like beam cross section. We have a moment acting on it. Magnitude of the moment is given. This profile is made of two L-shaped profiles, L profiles, and these L profiles are connected with a plate through the rivets or some bolts, and we are asked for the moment carried by this plate which is at the center. Okay, so in order to do this, first thing that we have to do is we have to find the stress distribution through the profile. Therefore, we need to calculate the centroid because profile is not symmetric. In fact, the centroid or natural axis is not at the center. And second thing, we have to calculate the bending moment of inertia with respect to the axis which passes through the centroid. Let us define the variables for this purpose. First, we will draw the profile. So we have a T-like profile. It is something like this. So we have two L profiles and one plate. We have thickness here. Let's say that this is T1. We have a length here. Let's say that this is H1. We have this distance, this dimension, which is B. Then we have the thickness of the plate. Let's say that this is T2. We have the total height of the plate. And we will say that this is H2. In fact, cross section is symmetric vertically. So T1 is equal to 10 millimeters. T2 is equal to 20 millimeters. B is equal to 150. H1 is equal to 150 millimeters, and H2 is equal to 300 millimeters. Now, this is our geometry. Okay, we need to find the centroid. In order to do this, first we have to define our reference point. I will choose the bottom of the profile as my reference. Now I will calculate the centroid. Remember that centroid is equal to moments of the areas which forms the cross section divided by the total area. So first I have this plate which is at the center. Its area is equal to T2 multiplied by H2. Its centroid is located at its center. It is H2 divided by 2. Then I have these two L-shaped profiles, and it is made of two areas in fact. So it is 2 multiplied by, I will just write the expression by 2 since the cross section is symmetric. First I have this area which is horizontally aligned. It is B times T1. Its centroid is located at H2 minus T1 divided by 2. Then this vertical area, it is H1 minus T1 multiplied by T1. So this is T1. And its centroid is located at here. So multiplied by H2 minus T1 I don't have the space here, minus, so let's write this expression below. Anyway, I will rewrite the equation down here. I don't have the space to write it clearly, so it is T2 H2 divided by 2 plus 2 multiplied by B T1, then it is H2 minus T1 divided by 2 plus H1 minus T1 multiplied by T1 multiplied by H2 minus T1 minus H1 minus T1 divided by 2. And then we will divide it by the total area. This is T2 H2 plus 2B T1 plus H1 minus T1 multiplied by T1. So this is the location of the centroid. If you put the values, you can easily find the location of the centroid with respect to the bottom of the cross section. So let me repeat it again. So in fact, we have T-like profile. First I write the moment of this plate which is at the center. It is T2 H2 multiplied by H2 divided by 2. So H2 divided by 2 is the location of the centroid with respect to the bottom, with respect to my reference point. since I have two L-shaped profiles on both on the left and right side, I just multiply it by 2. Then I calculate I take the moment of this area, which is horizontally aligned. It is B times T1, its area. Its location of the centroid is H2 minus T1 divided by 2. So the coordinate of this point, coordinate of the centroid of this area. Then I continue and I calculate the moment of this area. So this is the area is H1 minus T1, this distance multiplied by T1, the thickness, multiplied by coordinate of the centroid of this area. So it is H2 minus T1 minus this distance. So this distance is basically H1 minus T1 divided by 2. And sorry, this is H1. Okay. H1 minus T2 divided by 2. So from here, if you put the values, you can calculate the location of the centroid, the value for the centroid. Now let's calculate the bending moment of inertia for this cross section. I will calculate all the bending moment of inertia with respect to centroids. So we already found the location of the centroid. So first I will begin by calculating the moment of inertia of this plate which is at the center. It is 1/12 T2 multiplied by H2 cube. It is the moment of inertia with respect to its center of this rectangular area, plus T2 multiplied by H2, distance of its centroid to the centroid of the overall cross section. So its centroid is located at H2 divided by 2 minus y bar square. So its centroid is located here. Perhaps the centroid of the cross section is somewhere here, and then this is what I have, plus 1/12. Now I will calculate the centroid of this L-shaped part. Again, I will first calculate the moment of inertia of this area, and then moment of inertia of this area with respect to the centroid of the overall beam. In fact, I have two L-shaped cross sections. It is 1/12. First, the width, it is B times T1 cube plus B multiplied by T1, distance of its center of this area to the center of the overall or total area. Its center is located at H2 minus T1 divided by 2 minus y bar is the distance plus 1/12 Now I will calculate the moment of inertia of this region with respect to the centroid of the overall cross section. That is 1/12 T1 multiplied by H1 minus T1 cube plus area multiplied by the distance. So this is H1 minus T1. The distance to the geometric center is H2 minus T1 minus H1 minus T1 divided by 2 minus y bar and square of this equation. So this is my bending moment of inertia. From here you can calculate the value of the bending moment of inertia. Now I know the bending moment of inertia, therefore I can easily calculate the stress distribution through the beam. So if this is my natural axis, certainly I have such a stress distribution. This point is 0, it is on the natural axis. Or centroid. Now for any point I can write, so remember that this is my y and this distance is y bar. So stress is equal to minus m distance to the centroid. Distance to the centroid is y minus y bar divided by I bending. Now I will calculate the amount of load moment carried by the central plate. In order to do this, I will just draw the center plate now. So it has a thickness of T2. This is my location for the centroid. And it has a height of H2. So remember that stress is equal to, moment is equal to minus y sigma dA. And this is the area. I can calculate the value for the moment. I know that stress is equal to minus y the moment applied to the cross section, that is m minus m minus multiplied by y bar divided by I bending. Now what is dA? That is the question. dA is an infinitely small area, and that's equal to T2 dy if we have a very tiny piece which has a thickness of dy. Therefore, bounds for my integral is from 0 to h2, and this is T2 dy. This minus will cancel this one, and if I do the integration, moment is constant, it's already given. So bending moment of inertia is constant, T2 is constant, m multiplied by T2 divided by I bending. This is y square, y cube divided by 3 minus y bar y square divided by 2, and this is from 0 to h2. If you put when y is equal to 0, this expression is 0, then it is h2, it becomes mtb multiplied by I bending h2 cube divided by 3 minus y bar h2 square divided by 2. Now you can put the values. From here you can calculate the total moment carried by the plate at the center. Okay, our problem is 658. The aluminum machine part is subject to the moment of 75 kilonewton meters. Determine the bending stress created at points B and C on the cross section. Sketch the result on a volume element located at each of these points. I will not draw the stresses on volume element, we will see it in forthcoming courses, but let's calculate the stress at point B and C. In order to do this, first thing that we have to do is to find the location of the centroid of this cross section, since it's not symmetric with respect to the horizontal axis, and therefore first we have to it's better if we define the variables for this reason. Okay, so we have a P-like cross section. This is our cross section. Now let's define the variables. In fact, this cross section is symmetric with respect to the vertical axis as seen in the figure. We have this dimension, this distance is given as 40 millimeters. Let's say that this is h. So h is equal to 40 millimeters. Then we have the thickness, T, and this dimension is also given as T. They are both 10 millimeters. And then this is given as 2T, or let's say that this is okay, this is 2T. That's okay. So these are my dimensions. T is given as 10 millimeters. First thing that I have to do is to calculate the location of the centroid. So centroid is somewhere here, the natural axis. Okay, now we will divide the whole system into sub areas. So let's do it like this. We have two areas on the left and right hand side which are vertically aligned, and one big horizontally aligned rectangular area. So remember that y bar is equal to sum of the moments of the areas divided by the total area. I put my reference point again to the bottom of the cross section. You can put it anywhere. As soon as you do the calculations, it's okay. So you will arrive to the correct value, but my choice is the bottom of the cross section. So first I will calculate the moment of these two areas, and 2 multiplied by the area is equal to h multiplied by t. This is the area of this part. Then it is centroid that's located at h divided by 2. Now I will calculate the moment of the vertical horizontally aligned rectangle. It has a thickness of T, right? So plus T multiplied by 1 to 40, and it's symmetric, so we have another 40 here, so in total it makes 8T multiplied by the location of its centroid. Its centroid is h plus T divided by 2. It's located at the half thickness. Then we will divide it to the total area. This is 2 multiplied by h multiplied by t plus 8t square. Then we find the location of the centroid. Coordinate of the centroid with respect to the axis which passes from the bottom of the cross section. Now let's calculate the bending moment of inertia. There are several ways of calculating it. So again, I will use the same areas. In fact, first I will calculate the bending moment of inertia of these two vertically aligned rectangles with respect to the neutral axis. So I have two areas, so I will just multiply it by 2. 1/12 width multiplied by the cube of the height, t multiplied by h cube, plus, now I need to shift it to the axis which passes from the centroid, because I already calculate the moment of inertia with respect to an axis which passes from its centroid. Therefore it is area multiplied by the distance, square of the distance, and square of the distance is equal to h divided by 2 minus y bar square. Okay, so this is the moment of inertia of the vertically aligned rectangles. Now I will calculate the moment of inertia of the horizontally aligned ones. Aligned one. This is plus 1/12. Width is 8t multiplied by t cube. Now I will shift it to the neutral axis, because this is calculated with respect to the centroid of this rectangle. So area multiplied by the distance square. So this is, area is 8t square multiplied by the distance. Distance is h plus t/2 minus y bar square. Now this is the bending moment of inertia. Now in the problem we are asked for the stresses at point C. Point C is located here, and stress at point B is located here. Okay, so let's calculate the stress at point C. Sigma C is equal to minus m. Distance of point C, it is h minus y bar, distance to the centroid, divided by I bending moment of inertia. From here you can find the value of the stress by means of Pascal, and you can calculate the stress at point B. Certainly it is again minus m h plus t minus y bar divided by I bending. Of course, stresses at point B is point B and point C is compressive, because we have to calculate the value. Okay, so let's leave it here. I don't want to make a comment.